So I'm going to talk about this really interesting paper from a few years ago, 2020. It's made a lot of impact in the space of model generalization and some a little bit in the sort of deep learning theory venue. So it's relevant to a lot of stuff that I'm interested in. And it's really directly relevant to a lot of the stuff that I've been searching in this sort of low rank dynamics that we observe in deep learning. So this is a really interesting paper for me. This is different than the one that I originally posted, which is like this really extensive survey of how this particular result from this earlier paper like impacted all of model generalization and like a lot of stuff. So it's a really great survey of that, but it's because it's so extensive, it would be hard to cover in a limited time. So I'm going to just talk about the original 2020 paper on neural collapse and what sort of the general principles are. And I think it's a little bit easier to understand, but still some sort of sophisticated notions that we can kind of use that people might find interesting. All right. So we know about model generalization, the general underfitting, overfitting trajectory that we get as you increase model complexity parameters. You'll get sort of worse generalization outside of a training set. The model will just learn to perfectly model your training set. This is well understood. We know this. And then more recently, people have been talking about this terminal phase in training, this overparameterization of models that can occur where you continue to train past zero error, and somehow you get this. In certain cases, you'll get this sudden rapid decrease of test error again, where the model is somehow reconfigured in order past the overfitting stage to actually somehow be generalizing. There's a lot of sort of discussion around why this occurs, and this paper is part of that sort of larger discussion, which I think would be a really interesting topic for like a survey reading group in the future, like this overparameterization and what causes it, where it changes and stuff. But this is just a particular kind of theoretical answer with some empirical validation to what overparameterization is and what exactly it's doing. And particularly, a particular note is going to be this notion of inductive bias that emerges in all sorts of ML models where you have, inductive bias just describing the way that your model will potentially generalize beyond your training data. And you could potentially have sort of variations in the, cues in training data or sorry, your test data that may still be representative of the full distribution that you're interested in, but might, sort of confuse the trained model because that model is sort of only cutting out a small set of the full possible hypothesis space from that training data. So your model is sort of, going to potentially lead you in some problematic directions. The big sort of straw man example from deep learning is texture confusion in a lot of the convolutional neural nets that exist out there. You have a cat with elephant skin, suddenly it's classified as an elephant, even though it still looks like a cat, just because the model is CNN is learning information about texture rather than things like morphological cues that you would look at this and say, well, it has cat ears, it's a cat, for example. And so this is all of the paper. Basically, this slide is everything that is described in the paper. So I'm going to spend some time sitting here and talking about this. Yeah, what's up, Eli? Right. So hypothesis space is sort of all the possible predictions that could be made from your data, right? In some way. I mean, if you have a more, what was that?
Parameterized models.
Say that again.
Parameterized models.
It's the space of all possible parameterized models that can, yeah, right, that can exist from the training data, right? The actual trained model is only going to carve out a small subset of this space.
Yeah, I say it because I think it's not, for me, the first time I heard about it.
Sure.
What is it?
Yeah. All right. So this is the sort of canonical slide of this paper and of this whole talk and this whole idea of neural collapse. So you have these four characteristic things that happen that characterize neural collapse. First is this collapse of class variability, where data samples will concentrate around the class mean. The final layer features will concentrate around the class mean. So you're looking at the outputs of some kind of linear classifier prior to argmaxing or prior to softmaxing or anything like that. The final hidden layer features will concentrate around the class mean. The variability of the features between classes, between separate classes, will disappear. This is this collapse of variability. I think relatively straightforward to understand. I'll talk about this graphic in a moment. And then we have this preference towards this structure, this geometrical structure called a simplex equiangular type frame. I think the way to conceive of what this thing is, it's a very jargony way of saying it's a very restrictive, subspace where you are, where each of the sort of bases that make up this subspace are going to be, or not, they're not really bases, but just each of the kind of characteristic vertices in this geometrical structure will be maximally separated by some huge angle. So if you think about R3, so you have X, Y, and Z axes are not quite a simplex equiangular type frame, but you can think of the axes as having that maximal, equiangular variance. They're not, they're maximally separated. Each of the canonical bases are that form R3. And then the simplex is just saying that they are concentrated around, like, within these tight balls within that sort of space of maximum angular separation. So it's just a really complicated way to say all the points are kind of clustered in these small balls that are maximally far in an angular sense from each other. Right. So I think that kind of simplifies it. And then there's this idea, this third principle of neural collapse, self-dual alignment. The columns of the last linear layer classifier matrix also form a simplex. They're dual vector space. They converge to the same simplex that we saw from, it's from the penultimate layer features. So these are from layer features that are input into your linear classifier. Those converge to an ETF. And then the columns of the last linear layer classifier matrix also converge to that same ETF under scaling. So it's you're just saying that they're also converging to the same separation, but it's just scaled up or down differently, right? And that's what it means by self-dual. It's nothing more complicated than that.
And this is only for the penultimate layer.
So that was the penultimate layer convergence to the ETF.
Right.
Right. And then the columns of the last linear layer classifier.
Right.
Yeah, also scale. Exactly. And then finally, we have this fourth principle, which is that the decision rule that is that these models converge to after training, the last layer classifier essentially acts as a nearest train class mean decision rule with respect to the penultimate layer features. And I imagine this is meaning in terms of Euclidean distance. I don't think it could be anything else. And so you're just doing something like a discriminant analysis kind of at the end of the classifier, which is kind of shocking, right? We think of, well, it's not too shocking. It's maybe shocking if you don't, well, I don't know. Is it shocking? Does anyone find that shocking?
Like, I guess you would expect the penultimate layer to be some sort of like interesting space with a lot of semantic meaning that we also understand. Like, oh, this is where cats are, and when you look at the bases of this space, then maybe this is ears, and this is, like fur, and this is. So I think, yeah, it's pretty shocking in that sense. I mean, because this would also mean that probably the dimensions themselves don't have that much of like a meaning, because all the points are in one point on the line of each dimension, right? So you don't have like some sort of like linear, like more fur, right? You might just have like fur or something, right? If it's like all
what I I've been imagining it is you're just doing this like all the neural networks are doing are clustering in the sort of best way for this.
Right, yeah. But you know what this classifier, that's kind of like, you know, like a linear and interpolable, which you would kind of guess because the last layer is linear, so there must be a linear relationship between the last layer and the output, and you would want it to be some sort of like nice, smooth manifold, but it's not.
Yeah.
That's the way, because KNN also doesn't really create a smooth manifold. That is like a non-infinite number of points.
Yes, so this is it's an interesting result. So I've just described everything that is in this paper pretty much. So that's it for the talk. There's not really anything else to talk about. I mean, I'm honest, like there's like the rest of the paper is just formalizations, relations to other work, which I'll go over. But really the thing to kind of look at is how they, I think, go through this and from a sort of like if you're interested in writing theory papers, you know, what is their empirical justification? How do they set it up? How do they, talk through the underlying theory? That's what was more interesting to me about this work. But just kind of looking at this animation is fun. You can see this convergence occurring, right? So we have the two classes on the blue and cyan stick poles are the class means, and the individual spheres or individual samples. The red stick poles are the believe the last linear classifier, and this ETI is the equiangular type frame, the simplex that everything is converting to. So you can see all the balls in individual samples kind of clustering around into this simplex, and the class means are also aligning here. I mean, that just makes sense, right? Because the classes are kind of squishing into this ball. All right.
So the blue class is like on the top, and this cyan class is in the bottom.
I think so. That must be what it is. So red ball, so blue. I was trying to pierce this part because there are two shades of blue, and it doesn't make a lot of sense. So right. Blue ball and sticks represent class means, and small blue spheres represent last layer features. And so I imagine the two different shades of blue must just be different classes, or maybe there's even three shades of blue.
Yeah, I was gonna say because there's one class that seems to be going into two of these like dimensions, and then one into.
Maybe then it's three. Maybe this is a third shade of blue, and it's just so similar to.
Yeah, it should actually be. Yeah.
That might be. It looks like it might be slightly different. I didn't see it on my monitor, but now that it's on this monitor, it looks like this other. There's like a laser pointer in this, right? So I can show the online people. Is there a laser pointer? No. Oops. That's good. It doesn't matter. But yeah, these three shades of blue must be different. I think that would only make sense. And then you have these converging to different balls that are like the classes are maximally separated. So you have these lying on this sort of basis that looks a lot like R3.
It also makes sense when you just think about the loss itself. Like it's not trying to maximize classification accuracy. It's literally trying to maximize like how far away the class is. Yeah. Because the best would be if they're all like infinity away. Right? That would be like the best softmax loss. Right. You get e to the power like, minus infinity for every one of them, and then e to the power is infinity for the correct class.
Yeah, that's exactly and that's I think you already hit on what is most of the justification for this work is that they say that this is all that we're doing when we choose a particular loss and we have a linear classifier at the end of it. Like it's not anything more complicated than that. So it's.
Is it also related to that like square loss paper that Sergey I think presented like almost a year ago I think, where they were like saying square loss is better than the classification loss because you get like a smoother.
For later, I'm sure. I don't know. So I think this paper is more loss agnostic than that would be, right? So yeah, this is just saying that they show it for cross entropy loss, for mean squared error, and for so only those two for sure. So again, the rest of the talk, I mean, if we wanted to go over it, is just like formalization. It's just all it is they're describing these ideas with notation. If you understand these ideas, this is the bulk of the paper. This is all of the results. you know, they have some empirical validation. So we have a formal definition of this the simplex with some terrible notation here that I don't like. They use some like logical operators as notation for vectors, which I think are they're just supposed to be like showing these are just like orthogonal bases or something. Like it's a really weird notation. But yeah. I tried to look, so it turns out this, I think what happened are these authors sort of stumbled on this notion of simplex ETFs in the mathematical literature, because there's a huge like area of discussion about simplexes and equiangulator type frames in mathematics.
Yeah, they probably use that as data.
Yeah, and so they probably pulled that directly out of this other literature. And so I tried to dig into that literature, but it's huge. I like was only looking at it yesterday.
It's like a base or something.
I must be. I can't think of anything else that it would be. And
It would be much nicer if they just do the Q or something.
yeah,
Like the Q or, you know what I mean? Like
Yeah.
we're used to things like Q being this. I'm not interested.
I can't think of anything like any other description for what that is. They don't define it anywhere.
It looks logical to use
Yeah.
if you think of it like as a matrix. I mean, it makes the notation.
Well, so it's an outer product. So it's a matrix and
Matrix times matrix.
yeah.
Or is it a vector?
No, it's a vector times vector, but it's an outer product of two vectors, so it's a matrix, right? And so that's why it's yeah, these are just components that are showing the
So then what are the entries in the vector? Because it's not a basis, right? Or it's like the outer product spans in space because it's like that's how simple it is. Just a linear.
I think this,
Doesn't it rank one if it's like two vectors without a product?
yeah.
So then it's not really a basis, right? It's just a single.
I don't know what it means. I'm like so like confused about it. I was trying to think about it and I thought I had made sense of it by saying that, you know, this somehow must describe this like maximum distance between you know, the bases. And it must, I mean, so I is the identity matrix, so that's gonna C is the number of classes.
In my head, it makes sense if it was a matrix, because then you can say like there's four proportional normal bases, and then you like do those together, you get some sort of like distance metric, right? With this. But if it's a vector, then it's just going to be a rank one matrix, which I don't know what that means.
Yeah, I don't know exactly what that is notating, but
M star is supposed to be a simplex matrix, some kind of a matrix representing this.
yeah. So maybe we need to go back. Maybe I'll go back and I'll dig back into the simplex literature and see if I can untangle or just find another definition which is equivalent to what they use here, but that uses clearer notation. And so we can really untangle what each of these elements mean. I don't think it's entirely important, but this is just for the sake of, you know, when you are writing theory papers, it's great to clear out your notation. It would have been better if they had explicitly defined every element in this in their caption. You define your notation.
I think it's also very odd. Like if it's something that, you know, like logically you can expect, that it seems to be, you know, especially if you take things from another field into a new field,
Yes.
make sure that from the new field.
Exactly. Yeah. All right, so we have some other standard notation for weights and biases. H will denote the activation. So then we have this, this is the object of study here is a linear classifier. So the weights applied to your input activations. So these are input activations from any sort of other encoder network. So you're just looking at like a CNN-based encoder maybe, or if you're doing recurrent learning, it's an LSTM-based encoder, doesn't matter. But so these are the activations from some other kind of encoder. You apply the linear classifier layer onto it, add your bias, and then you're just computing the loss, right? So this is pretty standard notation. See, we're not applying any like further activations to the linear classifier. This is very familiar to any of you that have worked with CNN, Cipher, ResNet has like linear classifier at the end of it. Everything, most of your like sort of computer vision. I think most of the networks we use here in our lab will have a linear classifier just tacked into this. So it's definitely relevant stuff. And some statistical notation. So they're going to denote. So this is just the average of the activations separated into the class means. So you're just splitting this by, into each class. Obviously, the sum of the classes will be the sum of the entire training. Standard statistical notations, but they explicitly wanted to define these in terms of these groupings. So the full training class covariance will be the sum of these, the interclass covariance and the intraclass covariance. So within classes and between classes, and they'll use these notions to describe. So this is the formal version of this slide where we just described everything in natural language. And so this is now the test of if you understand their notation. And then they have this this formalization twice in the paper. It's quite funny. So class, sorry, so I think I flipped these. I think this must be.
But it should be intraclass, right? Because the balls are very small. So
Right. Yeah. Yes, no, you're right. Yeah. So this is the collapse to the ball. So everything is collapsing to a ball. Recall what sigma W is. I've got to copy out sigma W, put it back in there. And then this is just the formalization of the convergence to the simplex. So maybe you guys can help me. Maybe this will help us untangle that simplex notation a bit. So we have this. So this idea that the difference between the class means and the global means are going to converge to zero. So we're going to say that this is like, so for one class, it's going to get some distance to the mean. Other classes are also going to get that distance to the global mean, right? And then this is right, that sort of maximum part of that, they're like constrained to extremities of the space, that the simplex structure. That's all that it's saying, is that they're all going to be, so this is like, you have like this idea that the space is like a pyramid or a triangle, maybe pyramid. I don't know, like the training mean is the center of the pyramid, and all of the classmates are going to be vertices on that pyramid. What was that?
they're equidistant.
Yeah, they're equidistant. Yeah, exactly. Right. So yeah, looking at this notation, I don't entirely know what it means. So this is the mu with the tilde is the normalized class mean. So you're is the normalized and centered class mean. So you're taking off the global training mean, normalizing it, and then you're saying that this between two classes, this the inner product between, so the cosine distance maybe will converge to this ratio of the between those two minus this this control term from
Yeah,
it must be
yeah, it kind of looks like they kind of did something about like mixing it and said, oh, it's kind of similar to how like the variance converges in linear progression.
exactly.
Because of the C-1. That's the big mean, right? And
Yeah.
variance that some people say it's with it converges with C-1, and some say it's converges with
Exactly. Okay. Yeah. Exactly. So this is just aligning with this idea that you're going to converge to this C-minus this 1 over C-1.
But yeah, I think yeah, because that would make sense, right? The Kronecker delta, you get like for each dimension, you get like one Kronecker delta, you just multiply that by C over C-1.
Right. Yeah. Moving on. So this is the idea of this convergence to self-duality. So M is just a collection of the that again that the weights on the linear classifier, the columns of the weights are going to be proportional to these these H's, which are assembled into these class means, centered. They are going to be proportional, right? This is this duality that you're just the columns, the classifier are proportional to the simplex itself. Okay, and then this is
Can you define that delta before?
M star was the simplex. So M star is the simplex. M, yeah, the notation's not great, but this is like, I think, as you get into higher mathematics, especially higher mathematics that is just applied to things that you're involved in, I think you kind of find that people just get into notations, and once you kind of untangle the notations, the principles themselves are a lot easier to understand. And a lot of the work is untangling notation. And that's a huge pain. And I think I wish that mathematics was less notation heavy, but you need it to an extent.
Yeah. I just feel like it's one of those things where if you apply something from another field already, you should like adapt the notation.
I think so. The problem is that there's not a standard notation.
I understand. Because it's new in the new field, you can just adapt your own.
Some results. And so I think what is best for us to do, the work that we can untangle here is, what do they do and how do they construct their empirical experiments to, their theoretical results. So they have general collapse condition that the class means and the classifiers become. I think that this should be equidistant instead of equinorm. I don't know why I wrote that. Norms, as well as the network classifier norms, particular. So you're looking at this standard deviation, the centered class means. The weights for the classifier. Where WC is the last layer classifier for the steep class. The standard deviation of these class means over the average of the norm converge down to zero. Okay, so they're saying that, yeah, so that the variation over the mean is going down to zero. What does everyone think about this? And more importantly, they're showing that this is occurring.
The fact that they're showing that they all collapse down to the means of the classes, is that the same thing as proving this ETF simplex idea?
So the ETF simplex, right, has these different characteristics. Let's go back to the natural language thing, and I was expecting to go back to this slide a million times. So the ETF is a symmetric structure whose vertices lie in a hypersphere, which are linearly separable and placed at the maximum possible distance. So they're maximally distanced, and they have the maximum angle of separation. and they're tight within these balls. There are these three kind of characteristics of
The NC1, right, which is
Yeah.
the collection variability.
exactly. That's what figure 2 is, just NC1, and figures 3 and 4 are going to be NC2. All right. Yeah, so this is figure 3. So this is the at here, we're looking at the cosine of the distance between class means for two different classes, normalized. Right, I'm looking at colors. So the put into the classifier, and again they're showing that these cosine angles, or rather the variation of these cosine angles goes to 0 again, so they're equal. I wish they had some. So it's actually quite interesting that things. So fashionableness is a great example with the SpeedGG network that you see actually after the 0 error training period, that then things really collapse to 0, at least in terms of the classifiers. It converged to 0, which is interesting. I didn't notice that earlier.
It does seem like they're converging, but like this would take very long.
Yeah,
So you can do the slide.
it's hard to
This
tell.
would be usually done.
Yeah.
Does that necessarily make sense in a really high dimensional space? Because, I mean, I can see it would make sense in lower dimensional space, maybe like 2 or 3 dimensions, but does the implication of like the maximum angle and maximum distance
So think about the notion of like what a like orthonormality is, right? So it's just that you have so like in R2, the x and y axis are orthonormal to one another, the maximum distance separated. And then if you expand that to 3 dimensions, that z axis is also orthonormal. If you extend it to R4, you're now creating the 4th dimension that is orthonormal to all 3 of those other vectors. So you can't visualize it in your head, but it does generalize this idea of maximum distance. The idea is that just that you could have a vector that is not completely sort of orthonormal, but it's going to have some other angle. So it's going to exist in this higher dimension, but it's not necessarily going to be a new basis.
Yeah, that's what I was actually just thinking is like kind of what they're saying almost is like you could thing, which also kind of connects again to what Pablo and I presented on, which was called again superposition, where they could have also what they did in superposition was they calculated the correlation between each column.
Yeah.
Like you would expect here that correlation also essentially goes to 0 because because it should map a different. If they're like maximally equal to each other and they kind of span different bases, then the mapping from that each basis to the class should be independent.
It's not unique though, right? Is what you were saying with the superposition.
No, exactly. Well, my point would be like we just don't know exactly like how these bases are rotated,
Right.
but because the simplex could be rotated any way,
Yeah.
and that's what the final classifier layer is doing. Is
Yes.
kind of what it sounds like they're saying.
Yes.
But so you could redefine it into because that also makes sense. Like that linear classifier is redefining it into like a basis with 1, 0, 0, 0, 0, because that's the minimum loss you could get. It would be to have a Kronecker delta exactly at the class, and then all zeros or minus infinity at the other.
Yeah, and it's a basis. So they're defining it in a basis of well, it's not necessarily going to be a basis, right? Because they're not Well, they should be, but close to a basis, right?
Yes, I mean, that's it, like,
Yeah. And they're also going to be like everything is kind of stuck within these balls. There's that additional notion as well that they're sort of clustered in these small regions at the sort of furthest extent of that the space. This is figure 4, which is showing the max. So this is showing this maximum angle. So this is so they're measuring here. So let's look at exactly what they're measuring. So it's this average. Oh, this is so tiny on this slide. I can't. It's the average shifted cosine, right? So they're looking at this cosine plus just shifted over. All right, so this is exactly what they're measuring. So it's the cosine of the angle plus 1, or sorry, plus 1 over c minus 1, and that's the orange. And then do the same for blue for the mean activations. So how is this showing? Sorry, I'm trying to differentiate in my mind what is exactly the difference between these. So this is showing the difference between class means. It's the same thing. So cosine is defined as before, it's just shifted.
I think the difference is that they're looking at the maximum angle, but the other one they're thinking like,
Oh, it's the 1 norm, or is that the absolute value? Wait,
if you click one, you can see that here it says maximum angle, and then the other one it says, or maybe back. So it's equiangularity, like not the maximum equiangularity, but just the.
all right, but it's, yeah, I see, that's the difference. So they're measuring, this is the variation, and yeah, okay, yeah, that makes sense. This is the standard deviation, and this is just, yeah, the angle. Right, okay.
Yeah, so that kind of makes sense, maybe that the standard deviation doesn't fully go to 0. Just because of like training is, once you're stuck in like some sort of like minimum kind of like that. Because this would be the standard deviation, right? Yeah. So that's why maybe it doesn't converge to 0 exactly. There's still some like deviation that's a little bit happening. It's like a not super stable point maybe.
Okay, but it's still it's always the maximum point. Seems. So this next one, these all go to, well, more or less to 0.
Which is also more convincing.
I was wondering when I first read this paper, I was like, why do they have these as 2 figures? I figured like you could have shown as 1, and so it's good that we untangled it a little bit. I think that makes more sense to me now. Okay. So this is the self-duality. So they're looking at the proportion between these two. So this is the assembled class means, this M tilde, which they've now overloaded M like 5 different times with the M star, M tilde, and dot. And I'm surprised there's not an M prime in here somewhere, honestly. Yeah, M hat. Every single thing you can put on a piece of notation, you got to put it there somewhere. And then W is the weights, and so they're just looking at the norm distance between these weights. So showing that these do indeed converge to something up to like a scaling. So quite interesting. And then this is the within class covariance. So this is the shrinking of that ball. Yeah, same thing, converges 0. Except for ImageNet. Because they shrank quite badly on ImageNet, I think, and CFAR 100 as well. And then this is showing, okay, so I was interested in this as well to show how they showed empirically that the classifier just becomes sort of a linear decision. We're also running short on time, so I might just end after I show this result. I see. So they're just showing, they're choosing the distance. This is proportion mismatch. So they're let me see. What exactly are they measuring? I was really unclear what they do. So they're just counting the differences between what the networks actually do and what you would get from choosing the minimum distance to the class mean. I see that. That's all what that is. And so they're just having each one make a decision. And I think just counting the differences. That must be what it is. And they're showing that these converge towards zero, especially with some of these are really clear after that zero error point. That's really interesting.
And for me, a little bit, if I can push back a little bit, is that I find it less convincing because the hardest data sets, which are image and CPAR 100, which is the ones where we really need neural networks, are the ones where this doesn't seem to hold true exactly. Like, MNIST, fashion MNIST, SVHN. Yeah, the best classification you could probably also get by just taking the class mean, almost, right? Because just thinking about MNIST, I mean, you can get MNIST 100% classification, I think, if you just draw a random number. But it's so simple, right? It's such a simple.
I think, I don't think they're saying that it's good that they do this, right? Or that it's good for training. I think they're just saying that this is what they do. Right, and it is this is even for ImageNet. You can see, although it doesn't approach zero, well, at least okay, zero's got to be done here. It doesn't approach zero exactly. It is approaching that linear classifier.
I guess it is after a whole neural network that they're doing this stuff.
Right, and so it's doing all the complicated baloney. It's it's after ResNet, it's after VGG, it's after DenseNet. So. That's what the analogy that I think Sergey has told to me is that the encoders are doing their best to make everything about the data set into a linearly separable space, and then the linear classifier is just linearly separated in space.
So that's why I'm saying that you would want that space not to be like this, right? You would want it to be a smooth manifold, but the loss we're using doesn't encourage that at all.
Okay. Interesting. Okay, so there's a lot more stuff. So this is they're measuring. They're doing some adversarial, inserting some adversarial test samples and showing that, this terminal base of training, makes things a little bit more robust to those adversarial examples. They have a beautiful table showing improvements, 1% improvements in test error, which are what when you cattle competitions and stuff these days. I had a summary. There's a lot more to talk about. There's some connections to previous work that they show, but I'm not gonna go into it. Most of these previous works are all they're trying to characterize or what this class classifiers do, and they've described it in terms of max margin classifiers. They described it in terms of so this is looking at a nonlinear discriminant analysis showing the multi-layer classifier networks are doing basically NDA. And they just align this work with what those previous works have shown so that they're completely compatible with those theories as well. They do go a little bit to exactly how the simplex emerges, but I didn't look at the proof for it. I think it would be good to look into them and also clarify some of their notation, but just for the sake of time, we'll summarize here. So this paper is really looking at this terminal phase of training. And they claim that this neural collapse is really where that occurs in abundance. It had these these four principles that I think are very aptly describe this phenomenon. They claim that this is a clear demonstration of inductive bias in these models. That you're particularly rotating and confining the classifier to this really rigid geometric structure, right? It's a formal way to describe the bias that these classifiers are prone to.
So do you think that if you don't have this very rigid geometric structure, and let's say have very smooth, that would help with generalization?
I mean, they would I don't potentially I don't quite know. I mean, so here the argument is kind of that it's this phenomenon that even lets terminal phase generalize as it does. So saying that this is I think the best characterization of the space that can be obtained for a linear classifier, right? What I would more say is that I'm interested in, are there ways we can I mean, are we losing anything by forcing this, by forcing things onto this structure? I don't particularly know.
I guess it depends a little bit, like image I've obviously looked at this data set. If you just think about, medical data, there's so much like variety in new people coming in that you probably don't have any training set that just such a strict geometrical structure, it's going to be mapped to either one of these means, and you don't get a lot of like information about like how close is it to the mean, right? Like that's I think an issue. It's also why we need conformal prediction and stuff like that, to get like some sort of picture. How confident are we in these predictions? I guess it's like perfect if you want to get like 100% accuracy, right? But for real life setting, you can make the argument that it's almost better to know, how it's doing on features, right? Like in a smooth way, you can just know what these features are. But it may almost be more interpretable. But yeah, no. I think it is like one of, it's the most efficient almost form of like getting perfect classifications for it.
Yeah, it seems like it. I mean, I wonder like if you were pushing things into a space where a linear classifier would fail, what geometric structure would emerge and what would be gained? Is there anything even gained from that? I highly doubt it. Or not highly doubt it, I somewhat doubt it.
I guess it also depends on what type of linear classifier you use, right? Because if you use the SVM, that would have potentially created a different type of simplex. Right?
Yeah.
Because now you have a hybrid plane. You don't have a
So yeah, yeah, interesting work, but yeah, we should be done. I mean, this is certainly related to this rank deficiency stuff that I'm interested in and a lot of other related problems. Yeah, thanks for listening, folks. I think it's an interesting body of work to continue looking at. Let me know if you want to talk about it some more. Stop the recording.